All right. Good morning, everyone. Let's get started with today's exercise or today's lecture. So I just recently uploaded this presentation to the website, and I noticed that I forgot to give you a link to it actually. So I just shared the link on your emails. Yeah, just send an email with the link to this presentation. Again, it is an HTML presentation. If you want to download it and take notes, you can do that on your site. All right, so today we're going to be talking about a lot of topics in machine learning. I try my best to compile different sources here and make this as simple and straightforward as I could. However, I'm sure that there's still a lot of things that may come across perhaps not very clear. And I do ask you that if something is not clear, feel free to raise your hand to ask a question. My goal is that you understand here. And today we're going to be talking about some of the concepts that will really define how we do machine learning on the next class moving and forward. And so, please let me know if something is confusing. I would be glad to take the time and stop, revisit, maybe explain in a different way, so these concepts may click more easily for you. All right, so the goal of this presentation here and today is to talk about what is machine learning, what sets it apart from other types of analysis. Understand especially, so this course here, the way that I designed this semester was that we spent, the first half or perhaps a little bit more than that, the course talking about experimental design analysis applied to agriculture. The middle part of it being more data science as far as retrieving data, feature engineering, and so on. And now getting to machine learning models and how to train them. So one of the questions that I asked myself a lot when I was learning this is, what is the main difference here between all the models that we learned until this point and machine learning models? So what sets them apart? That's something I want to just briefly touch base on today. We're going to look at a machine learning workflow from beginning to end, and addressing the different pieces of it, different concepts that go into creating a machine learning workflow. We're going to talk about variance bias trade-off. This is a very important concept in machine learning that we're going to see some examples in the lecture today, and we're also going to be addressing them in our exercises when we get to the point. If you ever, I did a few job interviews when I was applying for jobs after grad school that were in industry and were data science related. This is a concept and one of the questions that all the interviews I did were asking about. So it's something that's important for you to understand, important for you to know what this is and how it can impact your models and how to address that. In relation to that, we're going to be talking about data spending, how we use the data we have in different parts of the machine learning workflow, some training techniques, and then hyperparameter optimization, and finally predictive assessment. So overall, some of these components here are going to be part of the machine learning workflow when we get to implement it with code. So that's why they are in this order here, and you're going to see this again as we do the exercise next class. All right, so what is machine learning? I guess there are different concepts about this. This is just one excerpt that I got from one source, that really machine learning is a subfield of artificial intelligence, which is broadly defined as the capability of a machine to imitate intelligent human behavior. To our extent, and to the extent that I normally use machine learning in my approaches, I don't ever really see this as trying to create like a random forest model to imitate intelligent human behavior. Perhaps this is something more towards deep learning, which is also a part of machine learning, but we're not going to get into deep learning to this course. We're going to stay within machine learning algorithms and some of the most common ones in agriculture, especially with tabular data, which is what we have. If you don't have tabular data, if you have especially imagery data, text data, or something that is not as structured as tabular, deep learning is probably going to be a better option, which again is not something we're going to cover in this class. but just so you understand some of those differences even within machine learning. So with tabular data, we're going to be using popular models like random forest, different types of regression models, other types of tree models, ensemble, bagging, boosting trees. So these types of models that have been widely used with tabular data. Now, if you do have, other types of data, again, like imagery, sound, or text, or other things that are non-structured or not structured in a table format, you would definitely go into deep learning. And there are other courses here, UJ, that you can take for that. All right, so the first concept here that I want to make a distinction of is what is going to set apart the models that we're going to learn now from the models that we already learned in this course. Anyone has any thoughts here? What do you think that a random forest model, or how do you think a random forest model is different from, like, let's say, a completely randomized design model?
One is more predictive.
Which one? Yes. So normally we would think of experimental design models as being used for inference, right? So we're trying to understand what happened in that analysis, in that study with that data, using a model that's already predetermined. Whereas machine learning, even though we can also use for inference, but the term machine learning itself is more related to prediction, right? So trying to create a model that, yes, looks at past data, but also is used to predict new data that it has not seen yet. So for the most part as well, on the experimental design side, the model is predetermined. And that's something that we talked a lot about as we were going through those exercises. So if you remember, we had a specific model for CRD, a specific model for CBD, for split plot, and so on. So the model is predetermined, and we don't really, there's very little room to play around with the model, to add things, to remove things, and see what creates a best fit, because that is not the goal, right? The model is something that you should determine when you're planning the study. So even before you collect your data, you should already know what model you're going to use, because again, model is connected to the study design, which is part of your treatment design and experimental design. Perhaps one exception to this rule of not having room to play around is when the assumptions do not hold, right? So the assumptions of linear model that we already talked about a lot, if those assumptions, you check for them on the residuals and they do not hold, we have some flexibility to play around with the model. And one example was repeated measures, right? So if you remember, repeated measure, we are coming in with the assumption that the independence assumption of the linear model residuals is not fulfilled, because you have repeated measure, you cannot randomize time or space, and therefore you come in assuming that the residuals are not independent, or they may be dependent. So in that case, you play around a little bit with the model, but notice and recall when we were doing repeated measures, you're not really playing with the model as far as the fixed effect terms of the model. We're just trying to allow the error matrix, correlation matrix, to be more flexible, right? So it's not like we're adding things and removing things. It's just that we're allowing it to be flexible into different extents using different correlation matrices and seeing if any of them produce a better fitting model than the default, which assumes independence, right? So even though there's a little bit of wiggle room to play around with experimental analysis, experimental design analysis, but it's not like we're really trying everything we can and seeing what's the best. We have a predetermined model. We're just allowing a part of it to be more flexible. On the other hand, with machine learning, we have a lot of room to play around. That's what machine learning is playing around with your data and your model, right? So we can play around by choosing different algorithms. So I mentioned a few just a moment ago. So random forest being a very popular one, support vector machine, lasso regression, ridge regression, elastic net, conditional inference tree, other like boosting trees. So there's a lot of different algorithms we can play around here and try. So just from if you think about it, the algorithm, it's almost like the formula that you had for a CRD or RCBD, right? So here you can play with all these options, whereas with experimental design, you had already a predetermined model to start with. As we're choosing different algorithms, those algorithms are going to have different hyperparameter types. So one example, so if you think of it, these machine learning models, they're going to have specific parameters that we refer to them as hyperparameters that control how flexible or rigid, or maybe how much of the data the model is going to be allowed to try to explain, given the hyperparameters of that model in specific. So a random forest model has hyperparameters that are different from perhaps an elastic net regression model. So different models that have different hyperparameter types, and then we can test different hyperparameter values within those types. And that's something we're going to talk a little bit later. So really, machine learning is all about playing around with your data, different models, different hyperparameters, trying to create the model that creates the best prediction based on your data. So this, I just want to kind of bring us back to this workflow here, which really applies to any type of analysis, not only a machine learning workflow analysis. But so this workflow here comes from one of the ebooks published by RStudio, where they bring this concept of the life cycle of an analysis. So we import data, we tidy it, we transform it, visualize, model, and stay within this part here to really understand the data. And after we come up with the best model, we communicate that all within a programming language environment. So this applies to any analysis, including the ones we have already done. But now, how does a machine learning specific workflow look like if we just take this template and we expand that into a machine learning situation? So a machine learning workflow, it can be more complex, it can be less complex than this, but in general terms, it's going to have three main pieces of it. One of them is the pre-processing, where we're going to do data split and data processing. We have done some data processing already that can happen as part of data wrangling, but we may have to do some extra steps when we get into a machine learning framework. Data split is going to be really important. We're going to expand that in a second here, but that is part of that pre-processing step. Then we get into the training side of things, where we're going to specify a model and perform hyperparameter fine-tuning or optimization. So this is really where we're going to take that model. So let's say a random forest model that if you just run with the default hyperparameter values, you're going to get a model. But perhaps if you change the hyperparameters to be a different value than the default values, you're going to get a better model or maybe a worse model. How do you know? That changes from data to data. And so we really have to do an exercise to find what are those best values that create the best model for your data that you have right in front of you. And then lastly, we do validation, especially assessing predictive performance on your model. So again, so if a person tells me they're doing machine learning and they don't really follow some of these steps, or maybe most or all of these steps, I'm not really sure if they're doing machine learning. So one example that I've seen in the literature or reading some papers is that some people may say that they ran as machine learning algorithms. So perhaps they're running, I don't know, random forest. Let's use that, I guess, as a recurrent example here. If they're not doing some of these key steps here and showing me the performance of that model for prediction, yes, they're using random forest, but is that in a machine learning setup? I'm not sure, because really for this to be, so to me, machine learning is all about prediction. For you to create a good machine learning model for prediction, you have to do proper data splits. You have to optimize hyperparameters or find the best values of them, and then do a predictive assessment of the model that you created. If you're not doing some of these steps here, you may be using a machine learning algorithm, but you may not really be using that in the way that was intended as far as creating a model that is good for prediction. Okay, so now I want to get into different parts of that workflow and dive a little bit deeper talk about some of the concepts, some of the options we have, and just further developing this workflow here. So on the pre-processing step, so the first step, I want to talk about data split for a second. So again, a major goal of machine learning, and one of the main differences also between machine learning and experimental design analysis, is that we want to find an algorithm that most accurately predicts future values based on a set of features. So prediction of future values is a key term here, right? So we want to be able to create a model that is generalizable. Or in other words, I give it some data and I train the model, but I do then want to use this model that I created to make predictions of future data that I don't know what the answer is, right? So let's say in our example of predicting cotton fiber strength with all these weather variables. Okay, so the data that we have right now, I have a column for cotton strength and I have all columns for weather variables. So I can create a model that can predict cotton fiber strength with the weather variables. But now let's say that, perhaps the top 3 variables explaining cotton fiber strength, let's say it was like temperature, precipitation, and solar radiation in May. Like a very simplistic model I'm just making up here. Now I want to take that model and I want to take these variables, precipitation, temperature, and solar radiation in May, and this year make a prediction of what my quality is going to be at the end of the year. So I don't know my quality yet, right? I want to make a prediction. So for me to make sure that my model, yes, was good in explaining my data that I had at hand, but is also a good model to predict values that I don't know what they are yet in the future, that requires a model that can generalize to different situations and to data that it has not seen yet. Connecting these points, we have to think of how we spend our data in a way that helps understand how well this algorithm is going to generalize to this new data. So one way, probably the simplest way that we can think of this, is that we're going to have to split our data into 2 pieces: training data and testing data, right? So we take all of our data. So let's say in our case, we have 698 rows. We split that into 2 buckets. One we're calling training data, which is going to be the data we're going to use to train the algorithms, fine-tune hyperparameters, and so on. And the other part of it is the testing data, which is we're going to hold the test data on a different bucket, on a different room, in a different building altogether, and not show it to the algorithm until the end, until we come with a decision of, okay, using the training data, I come up with this best model. And this model is not changing anymore. Now I use my test data. I use this model that I selected with the test data to check how well my model can predict the test data, given that the model has never seen the testing data before, because we split it and we kept it completely separate. So I guess just in text, the training set is what we're going to use to develop the feature sets, train algorithms, fine-tune hyperparameters, compare models, and etc. So all the process of creating a model and selecting the best model is going to be done with the training data. And then the test set is going to be, after we select our best model, then we use that model to predict the testing data and use the comparison between what the actual value of the testing data is and what the model is predicting, and the comparison to be able to say how well this model is predicting new data or unseen data, which is what we're referring to as the test sets. So one question that we can think about it in the sense of splitting data is how much data we're going to use. Because remember, so in our case, 698 rows of data we have total. Now, what proportion, what percentage of that total data are we going to dedicate to training and then to testing? That is an important topic as well. So normally, I guess I've seen these these different splits here of 60% of the data going to training, 40% going to testing, all the way to 70-30, 80-20. For what I do, most of the time, I use either 70% training, 30% testing, or 80% training, 20% testing. Those are the splits I most commonly use. But this is something that is an important decision to make as well, right? So if you spend too much data in training, so let's say you leave most of your data, over 80% of it in the training set, you will have more data to create a very robust model. However, you're going to have fewer data points to test if that model is actually doing good on unseen data, which is, again, coming from your test set. So if you have too much data in the training, yes, you have more data to create a better model, but also means to have less data in your test, which means you have fewer cases to test if your model is good. On the other side of it, if you spend too much data on the testing side, so let's say if you have over 40% of your data on the testing side, perhaps it's going to be harder for you to create a good model to begin with, because a lot of that data is going to the test, which is not using for training, just the training is used for training. So maybe your model is not going to be as complete as it should because it's not seeing enough data. But you will have a stronger test set to really test how well that model is doing. So this balance here between how much data goes into training, how much goes into testing, is something that we have to think of. And really the most common is probably 70-30% or even 80-20%, with the first number being what goes into training, second number being what goes into testing. All right, so we're splitting data, right? The most common way of doing this is just at random, right? So I take all my 698 observations and I randomly say 80% goes here, 20% goes there. That could work, and it is an approach that is used. But there's also another approach that's called stratified sampling. So for example, if I want to make sure that the data distribution of, especially, so in our case, fiber strength, right? So we're trying to predict fiber strength. If I want to make sure that the data distribution of fiber strength on my training set and my test set is the same, which they should be, I could do stratified sampling. If we do stratified sampling on a numerical variable, like is the case of cotton fiber strength, is going to make sure that different quantiles of the distribution are equally sampled and falling into both the training sets and the test sets. So this plot here I'm showing you is not fiber strength. Is an example I pulled from a different resource, where we're seeing sale price on the x-axis, which is the predicted variable. So imagine the x-axis here being fiber strength. And we're plotting here the density, so the distribution of that predicted variable, where we have two colors here. I'm not sure if you can see, but there's a black and a red density plot here, where one of those is the test set, one is the training set. This is what we would like to see, regardless if it's coming from random sampling or from stratified sampling. But we would like to see that the distribution of your predicted variable to be similar across training and test. Let's say if we do our split, we have, let's say 70% of the data on training, 30% of the data on testing, and we make this plot here where we color by either training or test to have a different density plot. And the distributions are different. This is something we can check at the beginning of the workflow. And if the distributions end up being different by random chance, that is going to be an issue for you, because you can train as hard as you want and create a best model on your train set. When you bring it over to your test set, your train set has not seen data like what you have in a test set. So it's going to be a very poor model, regardless of how much you can train it. So checking the data distribution when you do the splits and making sure that they overlap for the most part between your train and test is really important to make sure you're going to be able to create a model that can make good predictions on a test set. Another example or another way of thinking of this is imagine that you have this data, and then by random chance, it happens that your fiber strength values on the test set are all coming from Texas. And then everything else, all other states that we had, I think 10, 12 states in the data set are on your training. So all states on the training except for Texas, which is on the testing. Texas is a very different growing environment for any crop than many other states in the US. So if that is your case, just by random chance, your model is going to learn how to predict fiber strength in all states except Texas. So when you come on a test set and you only have Texas here and you use this model, it's not going to work well. It's not going to do a good prediction because it has not seen data like this before. Right. So just this is something that we want to keep in mind as well. In case you don't keep an eye on this, and it happens that your train and test set have different data distribution for your predicted variable, this is something that is called data shift. And again, we just talked about some of the things that can happen when that is the case. But the bottom line is you're not going to be able to create good predictive models and properly assess the predictive ability of those models in your test sets. So we want to avoid data shift, which is again, when the distribution of your predictive variable is different across your train and tests. All right, so we're gonna start talking here about hyperparameters. So now that we have our full data, we split that between train and test. We keep the test set completely separate. We don't look at it until we get to the end. So we take the train set, and let's say we select a given model type. Let's say we want to train a random forest, and we start the training process. So really the goal of the training process, and when we say training, what do you mean by training? Is it just fitting a model, or I mean, what is implied here? So training a model is really we doing an exercise of searching for and selecting the best hyperparameter values that will optimize model performance. When I say model performance here, again, is model predictability performance, a model that can make a good prediction on data that it has not seen. And if you have not heard of this term, hyperparameter is something you're going to hear a lot about when you're talking about machine learning, but it's really just a parameter in a machine learning model that will control how simple or complex the model is allowed to be. I wish I have, now thinking in retrospect, I wish I have had a different, or had a figure here to describe this. But one example here that I will say in words that maybe you can picture in your head is, so there's one model that I like a lot for reasons that we don't have to discuss right now, but it's called conditional inference tree. So it's basically just a decision tree model that is going to, imagine if you have like your data on the top, and then it's going to pick a variable and it's going to say, if this variable here is greater than, so let's say if temperature, it picks temperature. If temperature is greater than 10 Celsius, goes to the right. If it's less than 10, goes to the left, or guess right and left. And then it just keeps choosing variables and breaking down, creating a tree, right? Imagine that this model can be as simple as just having one variable being selected and breaking to two sides and stopping there. But it can be as complex as having thousands of breaks and going all the way down on the structure and being a very complex model. How do you know which is the best model? Is it the simplest one? Is it the most complex one? Is somewhere in between? So there is a hyperparameter on that algorithm that control, or maybe not just one, but many of them that control how complex this tree can be. And these are, again, called hyperparameters. So are things that you can change the value of that hyperparameter for that algorithm and that data set. And it will allow this model to be more complex. Imagine a full tree with thousands of breakpoints going everywhere, and one that is very simple, it just has one breakpoint. So I'm bringing here an example of random forest. I'm not fully introducing random forest in this lecture, so if you don't fully understand what these mean, don't worry, because we're going to cover this in the next coding exercise. But random forest has many different hyperparameters that we can play around and make the model more complex or simpler. Some of them that I normally tune myself or optimize myself when I'm training a model. One of them is called mtry, which is really a number that is gonna be the number of predictors, so the number of columns on our data frame that are randomly sampled for each of the splits of each of the trees. And the default value here is to be a third of the number of predictors. So in our case, I think we have like 70 predictors, something like that. So our, let's see here, 20, 28 perhaps or so. No, less than that, 25. Yeah, so in our case, this mtry value would be 25, approximately 25 for our data set. However, this value here could be 10, it could be 50. How do I know what's the best? I have to try different values and see what creates the best model. Another hyperparameter in a random forest model is the number of trees you want to allow to grow in the forest. So this number could be, as low as 10. So maybe just have a random forest that has 10 trees, and it could really go a lot larger than this. I'm just giving an example here of 10, 100, and 1,000. So again, how do I know what is the best combination of these two hyperparameters that are going to give the best predictive model for my data? You don't. You have to train your model. You have to find these numbers using the data, using the algorithm itself. So on the end of the exercise of the training phase, then we'll be able to say an mtry value of 32 and number of trees of 300 were the best combination for this model, this data. So that's my final model. That's how I train my model and then use that for making a prediction. So that's what the training phase is all about, is finding these values that control how complex or simple the model is, and then determining what those values are, and then using that model with those values to make predictions at the end. Now, what happens if we do not optimize hyperparameters? Which again, I guess when I was telling you before that when I see papers that tell me they use random forest, but they never explain how they train the model, I'm really thinking, well, you probably did not train the model, because if you're not explaining, you probably didn't do it, which makes me think that, this is not really a fully complete machine learning workflow. You're just running a machine learning algorithm, but you're not really training it properly for prediction, which is what machine learning is all about. So if we don't optimize hyperparameters, we may create models that are either too simple or too complex. And because of that, they do not perform well when predicting new unseen data. So optimizing hyperparameters is key in machine learning. And we're going to talk a little bit more about how to do that and some of the things to keep in mind when doing it. All right, so again, we have this conundrum of having too simplistic of a model or too complex of a model. We don't want either. We want to be somewhere in between, where we select and we train a model that fits your data very well, but it doesn't overfit. When it comes to that, this concept of variance bias trade-off is basically related to that. So when we have, remember, machine learning is all about prediction, right? So when we have the test set, which was not seen by the training phase, so when I was determining hyperparameters, the model did not see the test set. It was just a training set. So when I had this model that I trained on the training set, and I said, okay, this is my best model. Now let me check how good of a job it does on unseen data. And I use the model to make a prediction on the test set. That error that we're going to have on the prediction can be decomposed into three components: the bias, the variance, and irreducible error. Irreducible error is something that regardless of how much you train a model, it's not going to change. It's always going to be there. So we really focus on the bias and variance trade-off. So a model will never be able to optimize both bias and variance at the same time because they're inversely related. So we have to find a best combination of hyperparameters that puts us in a sweet spot on both of them. And that's a model that then becomes more generalizable as well. So start talking about bias here. So bias is the difference between the expected or the average prediction of our model and the correct value that we're trying to predict. So I have here a couple of figures where it's just an X variable, whatever it is on the X-axis, and then the response. So if I did not show you this plot or these lines yet, you know, maybe I would have thought that perhaps a quadratic response would be the best, potentially. But anyways, the model that's being fit here, I don't think is a quadratic one. So with bias, what is happening here is we get on the data set that we're seeing, we're fitting this curve. And we see that it's not really allowing enough flexibility to properly fit this model. Now, this becomes really important when we're then taking resamples of the same data set and refitting the model. So let's say what happened on the first panel here, we're seeing one realization of this data set and one fit of this model here on that data set. On the right-hand side, what you're seeing is basically what that model fit will look like if you pull 25 bootstrap samples. So we talked about bootstrap samples. It's just you taking samples from a data set with replacement, fitting a model, taking another sample with replacement, fitting a model, and so on. So what we see here is that this model on 25 different resamples, bootstrap resamples of this model, the line looks very similar. It's not changing from each one of the realizations of the 25 realizations that we had. So this model has a high bias because it's not changing as you're changing your sample that you're fitting the model to. And also it happens that this model perhaps is not the best one to describe this data because as we're seeing, the data has this somewhat quadratic response in the beginning that the model completely ignores. So we have a bias that is also not being able to capture the full signal of this data. Now, on the other side of it, we have variance. So variance is the error that we have, or the variability is the error due to the variance that is defined as the variability of a model prediction for a given data point. So let's say now I allow this model to be very flexible, way too flexible, right? I hope you can see that on the data here on the plot on the left side. So in one realization of this data set, you see how my model is touching many different points, right? So now it's being too complex. I'm allowing it to be too wiggly, right? In this case. And what happens then, what you see on the right side is on each one of the 25 realizations of the bootstrap samples, the model looks different, right? Because imagine you're taking a bootstrap sample of your data, fitting this model, which is way too wiggly. So when you compare the model wiggliness across any one of the 25 realizations, the model doesn't really agree too much, right? Because it's being allowed to model noise in the data. So it's going beyond just the signal, it's modeling the noise of the data. So when you have this model applied to different realizations of the data sets, you're getting very different models depending on what sample you got here on the right. So something to keep in mind is, so I guess just coming back here, this model has high variance. This model, so the first model I showed you has high bias. So it's a very rigid model. It's not being allowed to change much, even when you have different data. And it's also not capturing the full shape of the data itself, as we can see. This model here has high, or these models have high variance. So they're allowing to model too much. It's going like on the other direction. One is too simple, one is too complex. And by modeling too much, I have all this extra variance being produced on different realizations of the bootstrap samples of this data set. So still talking about the variance side of that trade-off is that many models are very adaptable and are really, really flexible. And that is a good thing because these models, like for example, random forest is very popular because it can model non-linearities in your data that maybe you weren't even aware. That's a great thing. However, we also need to be cautious because if you allow it to really explore all that flexibility, you're going to run into issues. And the issue you're going to run into is overfitting. So this term here, you're going to see a lot in machine learning as well. So this is overfitting, right? It is touching many of the points where it shouldn't. It should just give me the overall trend and not be touching many of the points. And the issue with that, and again, one reason why it's so important for you to have a test set, so have a training and a test set, is that if you overfit, you would not know you're overfitting if you're just using the training data, right? So let's say this is my training data, only this, so just think of this left side here. This is my training data. The more wiggly I make this line, the larger R square I'm gonna get because I'm explaining a lot of variability in my training data. However, if that variability has signal, but also has noise, which this one here has, when I bring new data that's gonna have a different noise, it's not gonna be able to fit on this curve very well because it's new data, it has not seen. And so this wiggliness that I allowed it to have was overfitting this data on the training set. But when I try to use this model, wiggly model, to make a prediction, the test set is going to fail miserably because my test set's going to have a different noise level. It's not going to be the same as my training. So even though if you allow your models to overfit, they will do a great job, high R square, lower MSE on your training sets. But remember, you're using your training set to create a good predictive model, and predictive models work well on unseen data. Your trained data was seen. You want to make a model that does well on unseen data, which is your test. So you may get really good performance on your training data if you allow it to be very wiggly, but it will not generalize well to unseen data. So this plot here really summarizes it, and it has a lot of stuff going on. I want to make sure that I walk you through this more slowly. So our goal here is to minimize the prediction error on the test set. So remember, test set, right? That has not been seen by the training phase of the model. For that, we need to create a model that balances well variance and bias. So let's just dive into this diagram a little bit and explain what's going on. So on the x-axis here, we have model complexity. So the more you go on the right, the more complex is a model. So imagine a model that is touching every single point, very complex. The more you go to the left, the simpler is the model. So imagine that first model we saw on the bias that was not even describing properly the shape of the data. On the y-axis, we have error. So remember, we are trying to minimize error, right? We want models that have low error to make a good prediction. Now let's look inside of this plot. So we have here the irreducible. If you remember, the total prediction error was bias, variance, and irreducible error. So our irreducible error is the dotted red line, which is constant. Again, it's not something we can really reduce beyond that point. It's going to be there as a residual anyways. And then we have, so let's look into our blue line here. So the more complex the model becomes, the higher variance we have. Notice how variance increases when you go from a simple model to a complex model. On the flip side of that is bias. So blue line is variance. On the flip side of that is bias. So bias is, so a large bias here is creating a larger error when the model is very simple, and then its bias decreases as the model becomes more complex. So notice again, the yellow line being bias, the blue line being variance. They are opposites, right? They don't go together in the same direction. So our goal as a data scientist, a data analyst, a researcher, is to find for each individual data set and each algorithm, where is the sweet spot where both of them are minimized. They're not going to be the minimum they can because, again, they're inversely related. So you have to choose one or the other. But if you want to optimize both of them together, we're gonna be within this window here where both of them, the intersection of the bias and variance happens. This is where we want to be. These models are the ones we want to create. And again, this is being controlled by how complex or how simple your model is allowed to be, which is controlled by the hyperparameter values you choose and you train that model on. And just a couple of other concepts here. Notice how the dotted black line is the error of your training set. So your training set, the error will always decrease as you increase complexity. Because you're saying, here's my data, use the data to create the model and then make a prediction on it. So it's like I give you a test and I give you all the study material and say, I hope you do well on this exam. You will most likely do well because I'm giving you all the answers already. However, that, if the goal is for the model to do well on unseen data, I mean a good predictive model, we need to look at the test error. So this here, the green line, is the error for your test set. And notice as well that it is minimized at that intersection of bias and variance. So this is basically the variance bias trade-off in a figure. And that's why we have to have a test set. If you're only calculating R square, root mean square error, whatever it is on your training set, you're fooling yourself because the more complex the model, the better you're doing. But if you're using this model for prediction, look at your prediction error. It's really high, right? So we want to assess our model performance on unseen data on the test set, which would be the green line here. Any questions?
So what are we referring the error here? Like, is it the residual values what is the error?
So, I mean, here is just error in general terms. It's not specifying a given formula, but it would, you can think of it as being the difference between your predicted and observed value. Could be one way of thinking of error. But this can take different forms. So one of the most common would be the root mean squared error. There's the mean absolute error. I mean, there's so many out there, but these are some of the most common ones that you would see. But I guess for understanding this is just the idea that we want to minimize the error of the prediction, right, which happens right here. And then whatever metric we're using, I guess it's not specifically important to understand this figure, but it will be when we're comparing models with the code. All right. So again, in other words, a model needs to be complex enough to capture the signal, but not more complex than that. Because if you allow it to be more complex than what it needs to be to capture the signal, then it starts capturing noise. And noise is going to change from one data set to the other, meaning that your test performance or predictive ability on the test set is going to be poor. So this is just, again, that same data set we've been looking at. And I think here they were training a K nearest neighbor algorithm where the hyperparameter that they are fine tuning here is K. So of course, we're not seeing here error, it's just the data with the model fit. So I don't want you to get confused because we're not looking at the error metric here. But if you're looking at this, if this is your data, we're seeing that the first panel here has K equals to 2. So let's say the hyperparameter K is allowed to have the number 2. And then 5, 10, 20, 50, and 150. This is one example of hyperparameter fine tuning. Although this is a visual example, I guess for the most part, we're not going to be looking at visual examples like this. But on this very simple example, if you had to choose a number, I guess we can really see how K equals to 2 is overfitting, right? It is touching many points here. It is fitting noise. Whereas K equals to 150, it's the most simple one, but it's really not fully describing properly the data, the shape of the data here, or the shape of this relationship. So if you had to choose in this case here, a K value for this data set, what would you choose? I heard 50, 20. Any other guesses? 50? Yeah, I think I would probably choose 50 and perhaps even a value between 50 and 150. So this is one thing that we're going to talk about in a second here is the way that this person was doing hyperparameter optimization is probably they used a grid where they gave the values of K going from 2, 5, 10, 20, 50, 150, and just evaluated the model at those fixed values of K. That is one approach. We're going to talk about that. But maybe there is a value between 50 and 150 that would create the actual best model that the person here did not try, but there are ways that we can explore that. But just, I would probably say if I had to choose, I would choose 50, but I still think that there is a value in between 50 and 150 that would create the best model possible. All right, so this is basically the variance bias trade-off visually, right? Where with 50 here, we're modeling the trend, we're not modeling noise. With 2, we're definitely modeling trend and noise. And with 150, I don't think we're even doing a good job modeling the trend. We're just way too simplistic here. Okay, so since high variance models are more prone to overfitting, we can use resampling procedures to reduce the risk of overfitting. Now, one issue that can happen here is many of these algorithms, including random forest, for you to be able to train an algorithm properly, you may need to fine tune a list of hyperparameters. Maybe it's not going to be just a single one. Maybe you're going to have to play around with 2 or 3 or 5, and each one of them are going to have many different levels as well. And so we can run into this issue here of having a lot of things to look into to find the best model. And I want to talk about a way that we can do that in a more in a correct way using resampling procedures of our data. Okay, so we already have our training test splitted. Now we want to use our train set to optimize different hyperparameter types and values and create a model that balances the variance bias trade-off and is a good model for prediction, which again is going to be based on the test only. Right now, this is how our data looks like, right? So we cannot touch our test set to train. So again, thinking of training this model, finding hyperparameter values that are best for this data, we cannot touch the test set. That's just for the end. So we need to use our training data only for this. How are we going to do this? How are we going to use the training data to find the best combination of hyperparameters? We're going to use a resampling method, and I want to show you a couple of them, a couple types. So let me expand this so maybe you can see better. So up until now, we had all of our data. We split into testing. So let's say 30% is here on testing, 70% is on training. Now on this 70% of my data that is under training, I'm going to pull different resamples from it. So let's say the first resample, I take a first resample, and that resample is further split into 2, where one of them I'm gonna actually run the analysis. So running a random forest with m try equals to 10 and number of trees equals to 100, let's say. So I'm going to create that model with this piece of the data, and then I'm going to use the assessment to see how well that model did. So it's almost like the assessment here is the test set for this analysis. The only thing is that this assessment is completely unrelated to this testing, right? Remember, the testing set, you do not touch until the end. Here, it's almost like we're doing a little test set for each one of the resamples that we have. What happens here is we have some data leakage into the training part of the model. What do I mean by data leakage? Because this assessment set for this resample, so let's say that, we do a resample here, and again, we do 70% of this resample goes into analysis, 30 goes into assessment. So I run this model with given hyperparameter values on this part, and then I assess R-square, RMSE on this assessment piece here. Now for the next resample, maybe there are some observations from this first assessment set that are now randomly ending on the analysis set of the other resample. That is what I mean by data leakage. You have some leakage here between the analysis and the assessment sets when you're training the model. For what we're going to do and what I'm going to walk you through, that is going to be part of it. We just have to be aware of it, that's happening. But always remember that even though you have some leakage of assessment and analysis across resamples, you still have your testing set that is untouched until the end. And that is what you're going to use to really assess the predictive ability of your model. So that testing set is not leaked into any part of the process. I guess I'm just putting here into words that for each one of those resamples, we're going to fit a model with a given set of hyperparameter values to the analysis part of it. So the analysis sets, and then check the quality of the model in predicting the assessment set for that resample, and then do it for all the other resamples as well. You have a question?
Is there any limit of a minimum requirement of a data set because we are dividing and if we have less data?
Yeah, I mean, I've seen numbers going from like the minimum being 500 to 1,000 observations. Obviously, the more the better until a point. But it starts getting very complex if you have very limited data. I mean, it becomes more difficult to train a good model if you have limited data sets, right? Because as you pointed out, Aminder, we are using this data in different steps. We're splitting it, so we're spinning the data in different buckets here. If you start having very few observations, it's going to be harder to train. I mean, the algorithm will most likely still run, unless you run into convergence issues on the resample levels. But it's going to be very limited what you can learn from a limited data set as well. Yeah, so I've seen numbers ranging from the minimum being from 500 to 1,000, depending on the algorithm. All right, so there exists many different types of resampling methods, and I want to list a few of them here and get into more depth as well. So the first one being a V-fold cross-validation. This is probably one that you're going to see the most in the literature. There is bootstrapping as well for as a resampling method for cross-validation, and there's leave one out cross-validation. What we're going to be using in the class for the most part is going to be V-fold cross-validation. So I do want to get into more depth on that. All right, so V-fold cross-validation is basically where, so V here is going to be the number of folds that you want to create, and I'll mention here in a second what I mean by folds. But basically, if you imagine that the figure on the left is all of your data set where you have 30 observations, so the number is the observation number. If I want to do a V-fold cross-validation where V equals to 3, so I have 3 folds, I would basically randomly assign each one of these observations to a fold, where in the right here, each fold is a different color and or shape. So we see here we have the folds that are green, and we see that observations 1, 3, 14, 15, and so on are on that fold. Then I have the fold that is the beige yellow here, where observations 2, 4, 10, 11, and so on are on that fold. And we have the blue fold as well. So if you have a V-fold cross-validation, where in this case V equals to 3, you basically split your data in 3 because you have 3 folds, and each observation is going to fall into one of those folds, as we're seeing here on this figure. Then what we're going to do is to train models where we're gonna fit, so let's say for the first fold, we're gonna fit the model to folds, I guess in this case here, beige and blue. So the model is fit with the beige and blue data points that fell on those folds. And then we estimate the performance of the model using the other fold. We do the same for the other two situations. So if we have three folds, you're gonna have three resamples, right? Where the first resample uses, let's say, fold 1 and 2 to train, and then test on fold 3. The second fold uses, let's say, fold 2 and 3 to train and test on fold 1. And the last fold is gonna train the model on the folds 1 and 3 and test on fold 2. So we're always keeping out just one of the pieces. So let's say if you have a 10 fold, if V was equal to 10, I guess 3 is easier to visualize. But if we think of the most common one is doing a 10-fold cross-validation. If you have a 10-fold cross-validation, it means that each one, the whole train set is going to be split into 10 parts. And each of the parts is going to be the test sets at each one of the stages. So you train the model with 9 folds, test with 1, and then you change which one you are testing on, removing that and doing that 10 times. So that would be a 10-fold cross-validation. In this case here, for simplicity, I'm showing you a 3-fold cross-validation just to imagine that concept. So, and I guess here is also another case that we can talk about data leakage, which again is only on the training phase we're having data leakage. But as you can see here on the first fold, so the green dots are not part of the training part, but the green dots are being part of the train set on folds 2 and 3, right? They're not being used as the assessment set for those folds, but there is some data leakage into the system. And this is what we want to avoid. So it's okay to have this on the training stage if you already split your data into training tests, right? Again, the test, don't look at it until the end. So you don't have the test set data leak into the training process. And in practice, values of V, so the number of folds, are most often somewhere between 5 and 10. And 10, I guess, is the most popular one you're going to see in the literature. On the flip side of that is going to be leave one out, cross-validation. So I don't have a figure here, but I do want to walk you through what this would be. So imagine that you have 100 observations, right? So in this case, n training set samples. So in my training set, I have 100 observations. This means I'm going to train 100 models. Why is that? So I take my 100 observations in the training set, I remove the first row completely, and I make a model, I train a model on 99 observations. Once the model is trained, I look into the one observation I removed and I predict that one. I make a prediction, I look at the difference between predicted and observed, and I put that in a table, predicted observed from this observation. Then I put this first row of the data set back into the data set, I remove the second row, retrain another model without the second row, predict the second row with this model, make a predicted observed, and do that 100 times. That's what leave one out cross-validation is doing for us. Where each model is going to make a prediction of a single excluded data point. And at the end of this, you're going to have n predictions that are pulled, and then you produce a single performance statistic that could be R-squared, RMSE, or others. So, Arminder, on your case, what you were saying, if you have small data sets, let me just come back here. If you have small data sets, let's say you have 100 observations, as in my example. If you do a 3-fold or even a 10-fold cross-validation, you will have a hard time training a model because you don't have too many observations to begin with. And you're very prone to the randomness of this process of ending with a test, or let me not use the test, then I get you confused. Using an assessment set that is different from the training set. If you have fewer data points, that data shift issue can happen here, which means that maybe your fold 1 maybe was a great model, but your fold 2 was a very poor model in the fold 3 as well. But it's all the same model applied on the same train sets, just different partitions of that. But because you have limited number of observations, you may end up with folds that are not representative on your training of the fold and the assessment of the fold. One way to overcome that is to use leave one out cross-validation, because now you have limited data, but you're creating many models where you're just leaving one observation out. So the chance of that one observation not being represented, or the pattern of that observation not being represented in the other 99 is very small, right? Because it's just one observation. So if you have very limited data, leave one out cross-validation can work better there. But overall, if you do have enough data, leave one out does not compare well for training a model when compared to other methods. So it's probably not something that would be highly recommended. V-fold cross-validation is what would be recommended if you have enough data. Okay, so let's say now, let's just walk us through again in this path here. So we have our full data, we split that into train and test. We keep the test set completely separated, we never look at it until the end. The train set now, we are performing a 10-fold cross-validation to determine the best number or the best hyperparameter values. However, we have not yet determined how we're going to do that. We just created the folds that we're going to use for doing that, but we have not further talked about how to do it. So we need to decide first which hyperparameters will be optimized. This is very important because this is going to change depending on the algorithm you're using. And also different algorithms are going to be more, within a given algorithm, there's going to be some hyperparameters that matter more to model performance than others. So we need to first identify which ones we want to optimize. Then we need to define what levels we want to optimize, right? So we talked about mtry and trees in random forest. So those would be the hyperparameter types, but then which levels within those types we want to test. And then finally, which optimization algorithm we want to use to explore that hyperparameter space. So let's talk about that here next. So in our random forest example, we had the two hyperparameters we talked about was mtry and trees. With it, well, I mean, I'm just, I guess, determining that we could try an mtry value of 10, 20, and 30, and trees of 10, 100, and 1,000. So how can so imagine that I want to run random forest models with all different combinations of mtry and trees. So that would be a 3x3, it's going to be a 9-level factorial, right? How can I test all those possible combinations and find the one that produces the most accurate model? Before I flip to the next slide, perhaps if we just think about it, right? If I tell you, Usman, if you're I want you to find the best random forest model for this data set, and I want you to try these different levels, right? So what I would expect you or anyone else to do is that you would run at least 9 models where each one of them is going to have one combination of mtry and trees. You run that model. So let's say model number 1 is mtry equals 10, trees equals 10. Run that model, use that model to make a prediction on a test set, look at what the predicted value is, compare that to the actual observed value, and do that for all the other observations. And then we can calculate how well that prediction is happening. So you do that across many of these observations for all of these different levels. So if we think of it, what I just described is what we call grid search. So in general terms, there are 2 different classes of hyperparameter optimization algorithms. One of them being grid search, the second one being iterative search. Let's talk about each one of them individually here in the next slide. So a grid search, what I'm showing here on this plot is basically, imagine I'm just showing 2 arbitrary hyperparameters here, one called parameter 1 on the x-axis, parameter 2 on the y-axis. The values that they take don't really matter. You can just think of those values being standardized values. Now, the points you're seeing on this inside the plot are the combinations of parameter 1 and 2 that I determined. So let's say mtry 10, 20, 50, and trees 10, 100, and 1,000. Those are the levels I selected. Those are the points you see on this plot. Now, for this illustrative example here, the best combination that produce, or the combination of parameter 1 and 2 that produces the best model is somewhere on the top right side of this plot. But perhaps not specifically on any one of the points that I selected. Maybe it's in between them. How do I find that? Well, with a grid search, you're really not going to find that specific level unless the level is one that you selected. But if the combination of parameter 1 and 2 that produces the best model is in between something you did not select, with the grid search, you're not going to be able to find it. So again, with grid search, we have a set of parameter values that we evaluate, and it can be inefficient because, imagine here, so we're testing mtry and trees with 3 levels on each one. But random forest really, I don't know, probably has 10, 15, 20 hyperparameter types that we can optimize. And each one of them, we can give anywhere from 2 to 100 values to try. So this starts getting very computationally inefficient if you're trying to optimize many hyperparameters at the same time. Or this approach of using the fixed grid search, which is very common. You're probably gonna see that in your in the literature as well. Another approach to this is using some sort of iterative search. So in this case here, we have the same plot. It's just that the points you're seeing on the plot are different. They're located in a different space of that bivariate distribution of parameter 1 and 2. So on an iterative search of any sort is going to sequentially discover new primary combinations based on previous results. And depending on which algorithm you're using that is iterative search in nature, you may have to provide a fixed grid search to begin with. So you say, maybe you give a very simple grid with a few values so we can start with. And then it starts with the grid, but then it starts to search for other potential values, which direction of the space here that you're going when you're thinking of these 2 parameters, which direction should it go to optimize the performance, even if that direction in the next combination of values that it tries may not be one of your actual provided values, maybe in between them, but it's going to be able to find it itself. So in this case here, in this example, it started, so the values that were given, maybe a few values here on the top right. So one thing is, notice how the search in this case did not explore the full space of both parameters, which in grid search it did, right? So you're estimating your model performance with hyperparameter values that are not even close to the optimal values, which again, the optimum is on top right. So why would you try here if that is not even a good point? Well, because you don't know beforehand what is a good value for those hyperparameters. But in this case here, on the iterative search, you provide some starting points across this bivariate distribution of both parameters, and the algorithm itself finds the way to the best values, which again are on the top right of this example here. Notice how on the iterative search, it did not explore this part at all. It has no combination of parameter 1 or 2 in this space here, whereas it was kind of going through the highest performance here until it landed on the top right, which is the values of parameter 1 and 2 that optimize a given metric. Could be R-squared, could be RMSE or other. So a couple different types of how we can do that search, right? So again, I'm repeating myself, but I hope that helps you to understand. So all data was put into train and test. We ignore the test until the end. We use the train data. We further split it into different pieces so we can find the hyperparameter values that optimize the model. We have different resamples here where we have for each resample, we have the analysis and the assessment sets. On the analysis set, we run each one of these combinations of different hyperparameters and we test or we assess the quality of that model on the assessment side. Do that for each one of the resamples as well. And then in the end, across all these resamples, across all these data sets, we're gonna have this combination of hyperparameters that optimize model performance on the assessment set most of the time. And that's how then we determine what is the model we want to use to say, this is my final model. Now let's bring the test set and just see how well it does there. Okay, I think I just have a text saying what I just said there, so I'm not going to repeat that. All right, so how are we then selecting the best hyperparameter values? We have, anytime we're making a selection, we're choosing something that we are judging to be the best or the worst or whatever it is. We have to use some metrics to do that. There are many metrics that can be used for that. I want to show you here a few of them that I have been mentioning already in this lecture. So one of them here is going to be R-square, which is the proportion of the variance in the dependent variable that is predictable from the independent variables, where the larger is better. So I want to have a high R-square of the relationship between the observed value that was actually measured. So what was this fiber strength measure from that field with what the model is predicting for that to be. So I want this agreement to be high. I want R-square to be high. Another metric here is the mean squared error, which is just the average of the squared errors. There is a formula for that. I can provide you with some references if you want to see the formula. I don't think you're going to have to use the formula yourself because we're going to be using functions that do that for us. But in this case here, the smaller the value, the better, right? So we want a large R-square, so a large agreement between the observed and the predicted, but I want that agreement to have very low error, which is one of the ways to assess that is using mean squared error. However, mean square error is a metric that is not in the units of your predicted variable. So mean square error is going to be, I think it's unitless. So it doesn't have a unit that you can easily understand. Root mean square error, so RMSE, which is just taking the square root of the MSE metric, is a very popular metric for communicating the error of a model. And one of the reasons why it's popular is because the units of RMSE are the same units as your response variable. So if I have my response variable in cotton fiber strength in grams per tex, RMSE is going to be in grams per tex as well. And in this case here, because it is an error metric, also is smaller is better. So I'm giving you here 3 metrics. There are many of them that we could spend probably a whole lecture talking about different metrics, but I just wanted to show you and tell you some of the most popular ones. And I want to call your attention to one thing here. So these metrics we're going to be using in 2 different places here. So one of them is on the training phase where we take our train data, do different folds, do different resamples, do a analysis, use the analysis data to train a model and then test that or assess the quality of that model on the assessment set of that resample. And this agreement between on that resample, this analysis set and this assessment set, I'm judging that based on R-square, MSE or MSE, maybe something else. So we're using these metrics on the training stage to find the best model with the best hyperparameter values. At the end of the training phase, you will say, this is the best model with a given value of MTRI, a given value of trees. Now we use this model to then make a prediction on the test set. And I compare the predicted and observed values using the same metrics. So the metrics are going to be similar that you use to choose the best model and also to assess the quality of the model in the end. It's just that you're using different using these metrics in different stages and with different splits of your data. All right, so let's say that we got to the end of our training phase. I was able to find a random forest model that optimized the prediction accuracy on the train set, even though I was doing the V-fold approach. And that model, let's say, was mtry equals to 23 and number of trees equals to 530. Let's say that was my best model. Now, as I was telling you earlier, I need to use that model and apply that to my test set to check model performance. So once we have found the best combination of hyperparameters that optimize model performance on the train set, which we're splitting analysis and assessment sets, as if you recall, now it's time to use this model to create predictions on the test set, which has not been seen yet by the model. And again, a very key important concept in machine learning is because the model training process has not seen the test set yet, the predictions that we make using this model on the test set are what will allow us to make inference on the predictive ability or generalizability of this trained machine learning model. So again, the test set, the training of the algorithm had not seen the test set at all. It's almost like if you had gone on the field and collected new data, right? Which is most of the time not the case, but it's as if it were. If you have fresh new data that the algorithm has never seen before, let's see how it does in predicting that fresh new data. So in our example here, we're using cotton fiber strength in grams per text. That is a continuous variable. And for continuous variables, the way that we assess model performance most commonly is using this type of plot, where we have the observed value on the x-axis, the predicted value on the y-axis, and we have this one-to-one. So we have a scatter plot of those points. We have a one-to-one line here being the black line. And then we have a regression line fitting through the points. And in this case here, I'm showing you the equation of this regression, this red regression line with a whole bunch of metrics and their score. So why is this very popular? If you think of it, the more complex is the model you're training, a lot of times it's going to be very difficult for you to understand. Like some of these models don't really have, the model itself doesn't have an R-square value. So when I was telling you about R-square and RMSE, I'm not talking about R-square coming from random forest itself. I'm talking about the metric, in this case, R-square or RMSE, coming from this relationship here. So in our case, the observed here, you can kind of think of the observed being the grams or the fiber cotton strength, cotton fiber strength in grams per text. That is our observed value here. The predicted is what the model that I trained on the training phase is predicting that those cotton fiber strength values would be. And again, when on the test set, even though we do have a column that says grams per text, when you use the model to make a prediction on the test, you don't give those values to the model. You just give all the predictor variables. I just give all the weather variables, and I say, here, you told me that for your model, for this model, temperature, precipitation, solar radiation a given month were important. I'm giving you those. Now spit out a prediction for cotton fiber strength. That's what we're doing, right? And that is what the predicted y-axis here is what value the model is telling you that you would predict on a data set that it does not have the actual grams per text in it, just the weather variables. And so it gives us a prediction. We compare that to the actual observed values because we did have those predicted or those points for cotton fiber strength from the field, so we can compare them. For this type of plot can be made for any model, any machine learning model. Does not matter how complex or simple it is. You will always have a column of the data you observe on the field, and you always have a column of what the model is predicting, even if that prediction is super complicated. It does not matter. This type of plot you can always make. So in this plot here, what we're looking for again is that the points are very close to the black one-to-one line, meaning that they have a one-to-one relationship, which is what you want. You want your model to be making a good prediction in relation to what was the observed value of that observation. So we want an R-square that's high. We want any other metrics that are low. And there's a list here of some. There are many other metrics that we can also use. And again, just to remind you, in this case here, we're talking about a continuous variable as our predicted variable. So cotton fiber strength in grams per text is a continuous variable. If that variable would have been categorical, so let's say if I take all these gram per text continuous variables and I break it down into classes and I say from this value to that value is low strength, from this to that is medium strength, from that to that other one is strong or high strength. So now I break this down into categories and my predicted variable is not continuous anymore, but is categories. Then the whole exercise that we're doing here would be a classification exercise and not a regression. I guess we talked about this in the past a little bit, but in machine learning, some algorithms like random forest, if you give the Y variable as continuous as what I'm telling you, the example of grams per text as continuous variable is going to do a regression machine learning. If you give it a categorical variable, like if I take my grams per text and I classify into 3 classes and I give those classes instead of the actual numbers, it's going to do a classification exercise. This type of plot predicted by observed is what we do to check predictive ability of a model when the predicted variable is continuous. If it would have been categorical, it would be different metrics, different way of assessing that. And I'm not showing that to you right here, since we're not going to be doing that example in this class. All right, and then I guess bringing the same figure here, but just to finalize this thought that models with greater agreements between the predicted and observed, in this case measured by R-square, so the greater the R-square, and the lower the error metric is, are better models at predicting new observations. So we kind of wrapped up the whole process by coming to the end, using the model that we've selected as the best, given the hyperparameter values that we tried, using that model to now make a prediction on the test set, which only now we're bringing the test set into the picture. We had not seen it, we had not considered it in any other step. Making a prediction on the test set, assessing the quality of the prediction. Every time I say quality, predictive ability, this is what I mean, is how well the predicted by observed of the model when predicting the test set is. So this is how we would compare different models as well. So imagine that now you redo this whole exercise with a different algorithm. So instead of random forest, you run, I don't know, let's say a lasso regression or something else. You would do the whole process and in the end have also a predicted by observed plot with different values for R-square and so on. But that way you can compare models and how well different models are performing on a given data set. So this basically wraps up the workflow of a machine learning model training and validation as well. All right. Well, I guess I just have a quick summary here. It just goes through everything that we talked about. Any questions? Yeah.
So for after predicting training set, when we will predict test set, so we have to, as you were saying, that put it through the same procedure, like analyze it, do analysis and assessment. We will apply the same k-fold cross-validation on the test set as well, right? Or
No, so the test set is, let me go back to that slide. So the test set, we only bring at this step here, right? So after you have already trained your model and determined what was the best hyperparameter values that created the best model on the training stage, only after the training stage is done is when you bring the test just to make a prediction on it, right? So if let me just go back to that. Yeah. So all of your data, you first split between testing and training, and then the training, you further break down on different resamples, where each resample is gonna be partitioned into analysis and assessment. So the assessment that we're doing to determine the best hyperparameter values are based on the assessment sets of each resample.
So this means we will compare the predicted values with the actual raw observed values in the test set. Is it?
Right, that's
Okay.
correct, yeah. Yeah, so if you imagine like on the, so whenever we do the splits, we're still gonna have the same number of columns, but just different number of rows, right? So let's say that we had, if you have 100 observations and you do a 70-30, then you have 30 observations on the testing. And one of the columns that you have there, that you have in both data sets, but including the testing, is gonna be like fiber strength in grams per text, right? You have that column, that's your observed. Now, on the training side, you do all this to figure out the best hyperparameter values of that algorithm. You determine which one is the best, and then you take the model, and then you come back to the test set, and you create a new column that you call a predicted, where it's taking each one of the weather observations of this data set and making a prediction for each observation of the 30 observations you had in the test. And then this predicted and observed, and again, the observed is the fiber strength in grams per text, is what you use in the end to make that predicted observed plot and calculate the metrics there. Any other questions?
Road distribution of your loans. Let's say that like in the plot that you show us the performance metrics. You have like high values, a lot of high values and some like small values, you have you put in square error. That would not be so useful for like the small values, right? Because it would be quite like high behind to those small values. What performance metric would you use instead? I don't know.
That's a good question, and I wouldn't know from the top of my head which would be the best one. I would imagine there is, let me just go back to the plot. I would imagine there is a metric that helps you there. So this plot I'm showing you here is from a package that I was a co-author, an R package that's called Metrica. And I think it has like over 50 different metrics for model agreement. And we published a paper on it where we explain each one of them. So I wouldn't remember from the top of my head what would be a metric for that case. But I will look into this and see, because if there is a metric, it's probably listed in that paper and as part of this package as well. Somebody had a question. Could you repeat the questions as, oh yeah. Yeah, it's awesome. Sorry for those online. So Jonathan was asking here that if you have, if you look at your predicted and observed plot and you have a lot of zero values, is that the
Yeah,
example?
low values.
Low values. So on the lower end of the distribution, you have many points here that the root mean square error of the entire regression would not fully represent the error that you're seeing for smaller values specifically. And if there was a metric that would better capture that. Yeah, so that was the question, if I got that correct. Yeah, so yeah, I don't know exactly from the top of my head, but if there is, I would definitely check that paper because there are many metrics there. Yes.
Are these metrics used to select the right parameter combinations? Yes.
Yeah, so you use the I mean, you don't have to use these metrics, they're just some of the most popular ones, but you would have to use a given metric in two stages. So one is on the training when you are comparing your different hyperparameter models. And so if we come back to that figure, you would use these metrics at this stage of the training when you're doing the comparison of your. So let's say again, for resample one, you're going to split that resample into two sets. One is analysis, one is assessment. So you use the data on this analysis set to train a model with a given combination of hyperparameters. And then you make a prediction of that model on this assessment set. And then you do that for many of those resamples and for all of the hyperparameter values you have. And in the end, you're going to compare how well or which combination of hyperparameter was the best across all resamples using one of those metrics, or maybe other metric, but a metric. So it could be largest R squared, it could be the lowest RMSE or so on. So we use metrics here on the training stage to determine what is the best model. And then after you determine the best model, you use again the metrics to assess how well that model does on new data, which is the testing. So we're using both in both stages.
The resampling and the hyperparameter selection happens simultaneously, right?
Yeah. Yeah, well, when we do the code, I think this is going to be a little bit more, well, I don't know. I hope it's going to be more clear, but it could be more complex as well because there's a lot of stuff happening. But yeah. Awesome. Any other questions? All right. I don't hear any, so I'm gonna take your attendance. All right, I just opened the issue. Make sure that you claim your attendance. Next class, we're gonna be implementing this workflow for our first machine learning algorithm that we're gonna be learning in this class. It's gonna, well, if any of you ever use tidy models, we're gonna be using that family of packages for doing this. And if you have not heard of it, don't worry, because we're gonna start that slowly next class when we train our first model. Right, if you don't have any other questions, and you have already claimed your attendance, then you are dismissed, and I'll see you on Thursday.